Taylor, please go ahead.
Okay, thank you very much. Thank you very much for inviting me to talk here. I'm very pleased and I'm very happy to be able to communicate on this subject. So the subject of my talk is about braided surfaces, which is some four-dimensional topology thing, and about their characteristic maps, which is, well, the characteristic maps are just some algebraic homomorphism from surface groups into some finite groups or whatever. And this is joint work with my former student, Pablo Pagotto. So to get started with, I'm considering two closed orientable surfaces, S and sigma. And what I called a braided surface over sigma is simply the embedding of the surface S in the product of sigma and a plane in such a way that when you project on the first factor going from sigma cross R2 onto sigma, the composition from S to sigma is just a branched covering. And this branched covering is called the characteristic map of the braided surface. So as I said before, we have phi, which is an embedding. So we can go the other way. We have a branched covering of two surfaces, S over sigma, by some map. And the problem we try to ask is whether we are able to lift it to some embedding of S into a thickened surface. This, of course, this is the more general question. Instead of asking phi to be an embedding, we could ask to be an immersion or whatever surface homeomorphism we would like or whatever. Now, as a four-dimensional object, we have to introduce some kind of equivalence among braided surfaces, which is usual just the one coming from ambient isotopy, which is fiber preserving, meaning that we have two maps, J0, J1 from S into the product of sigma and R2. Then we need to find some isotopy HT of the ambient space sigma cross R2, such that H0 is identity, H1 composed with J0 is J1, and is fiber preserving, meaning that the projection composed with HT is some map, some new map phi composed with P, where phi is going from sigma to sigma is a homeomorphism or a diffeomorphism, depending on the category we want. And when phi is actually isotopic to the identity, we say that the braided surfaces are strongly equivalent. So as I said before, one of the first questions we can ask about such braided surfaces is how many there are, and how could you relate them to the ramified covering? So in particular, as I said, going backwards and giving a ramified covering from S to sigma, can we lift it to a braided surface? And it's amazing that when we look to such question, we found that there is a lot of references, and it's in the case when instead of taking a ramified covering, we just took a generic smooth map. This question was explicitly raised by Sergei Melikov in, for instance, in a paper in 2015. But there are a lot of results in the Russian School of Mathematics around it. So I think you know here better than me. So I will stick to what I know, namely the case of braided surfaces. So this kind of objects were already known for some time. I think again, maybe among the first people working on that is Oleg Virov, late 70s and 80s. And then soon after that, there was some work by Lee Rudolph. Lee Rudolph, I guess in the 80s, 83, 85, who considered most of time the case of the so-called ribbon surfaces and surfaces which are covering the disk instead of our. So here sigma was just a disk. And then this was pushed much further, especially in the work of Kamada, and then Carter and Kamada in the 80s and 90s. So from 96 to up to date. And more recently, I think is Nakamura, who was interested in the case of braided surfaces over the torus. Before going further, let me make just a small remark, which is not that interesting, but if F was an unramified covering, and we want as the surface F as the lifting was not inside sigma crossers 2, but into some total space of a fiber bundle, total space of plane bundle over sigma. Then it was an observation of Edmonds, I guess is around 99, saying that if such a non-trivial example exists, then the Euler class of the fiber bundle, the plane bundle, should be torsion. So in some sense, maybe the most interesting case, if you want to go up to fiber bundles, is to stick to the case we have here, namely a product.
Excuse me.
Now,
What do you mean? So what is the hypothesis in Edmonds' theorem? If which example exists?
So you need to find non-trivial unramified coverings which lift to the total space of a plane bundle over sigma.
So for
not for all, but if there are unramified coverings.
I see.
That's already quite strong. That means that if you really have interesting examples, then better to consider trivial plane bundles, because in most cases they are not, or yeah. So that's a theorem of Edmonds. I can give you references later if you ask me about yeah. So let's go to recall that there is an equivalence for branch coverings, which is completely similar to that which you used for the braided surfaces. Namely, we have two branch coverings which are equivalent if there is such a diagram which is commutative like the one here, namely F0 and F1 gives rise to a map between the bottom surface and the top surfaces, which are homeomorphism. And in the case when the lower flower homeomorphism phi is isotopic to identity, we get strongly equivalent, and if not, it's just the usual, or also called let me put it here, Hurwitz equivalence of branch coverings. Now, in the case of surfaces and branch coverings, that's a quite classical subject on which, well, the first invariant which was introduced is simply the holonomy of the branch covering. So we are looking to the set B, which is the finite set of branch points of our ramified covering, and we have a map from which is the holonomy of the cover, which is the surface minus the branch covering minus the branch points. So here are the points P1, Pn, and any extra point here Q has above him a number, let's say n per image. So this the way the pre-images are permuted when we are traveling around one branch point corresponds to a homomorphism from the fundamental group of sigma, our bottom level surface in minus the branch points into the symmetric group on n elements if we have a degree n covering. So now what is known again since a long time is that branched coverings have a simple classification up to equivalence in terms of their holonomy homomorphism. So now here we have two kind of equivalence. So here is the usual, the Hurwitz equivalence. Hurwitz equivalence classes. They are corresponding then of branch coverings. So these are homomorphisms from the holonomy homomorphism from pi1 of sigma minus b into the symmetric group of degree n.
Sorry, Luis, can I ask?
Yeah.
If I have another order over market point, we have some gauge of this classification, and we will speak only with fixed number of pre-images over Q, yes?
Yes, yes.
Okay.
Yeah. So of course here everything is fixed, the number, the degree of the covering, and the number of branch points. Let's say the branch point is fixed given by m, and the degree of the covering equals n. And here on the right side we have the action by conjugacy of Sn, because of course changing the base point will change the homomorphism by a conjugacy on the right side. And I have put here some group gamma. Gamma of sigma minus b is just the mapping class group of sigma minus b, which is of course the same thing as the mapping class group of sigma preserving pointwise b. And of course the mapping class group actually is the automorphic group of the pi1 of sigma minus b, which is really acting on the left. But if you take if you take the quotient by the conjugacy, as I put up here, then the mapping class group, which is, I recall maybe just to say, this is the homeomorphisms of, let's say, sigma preserving point by P up to homeomorphism equivalent to identity, isotopic to identity. And if you don't want to look to Hurwitz equivalence, but just to strong equivalence, then you have to drop this action. But the most interesting case, and it's essentially on what we are looking at today, is this orbit set, which is a space. I'm saying space because instead of Sn, you can consider any other group, or it can also be a Lie group, and then you get some geometric objects there which are worthy to be studied. And actually, my interest in this theory arose from studying such kind of objects and the action of the mapping class group on it. So we are doing the same thing up here in the case of braided surfaces. So again, we have braided surface and we have a degree. And now we have again, there are two elements up here. Sorry.
So I'm sorry, there seems to be a problem now that, well, I cannot see the right-hand side of your nodes. So, for example, the third line is outside P, and then P from sigma cross R2 arrow, and then I cannot see where the arrow goes.
Maybe something happened. I'll try to do something. Let me put it up here. Is it fine now? Can you see up here?
No. Maybe you can somehow decrease the scale.
Yeah.
Okay,
that's better.
That's better. Yes, and you can still increase it. You can still increase it. It was yes. Okay.
Okay. Something happened. Yeah. Okay. So.
Thank you.
You're welcome. So now we have a braided surface. So as I said, is S, which is going to sigma cross R2, such that by the projection P, it arises in P, and here is the map. I call that F, and this phi, and F is a branched covering. And we call N the degree of S going to sigma, the degree of F. This is the degree of the braided surface. And now, outside the set B of branch points, so branch cover, over sigma, a branch set, branch locus B inside sigma, that outside B, you have just a fiber which is corresponding to sigma cross R2 minus S union P inverse of B over sigma minus B. And this is precisely no picture like that. This is R2, and you have a number of points here, the end points, which are over sigma. And these points can collide, maybe 3 or several, over a point pi of B. But outside that, everything over sigma minus B, we have a vibration whose fiber is R2 minus a number of points, which is coming up from here. And for this vibration, you just consider the holonomy of that vibration. Which I called phi star, which is a map, which is going now from pi1 of sigma minus B into the group of homeomorphism. Now, one has to be a little bit careful because I considered R2, but we can stick to the case when we have a disk. So outside the disk, nothing wrong happened. So you have the group of the mapping class group, or the group of diffeomorphism of a disk minus n points and up to isotopy. And this is something which is very well known, namely the braid group on n strands. So you have a map from pi1 of sigma minus B into Bn. And now one should remark that this homeomorphism is just a lift. So you have pi1 of sigma minus B, which has the branch covering holonomy F star going into the surface, into the symmetric group on n elements. And what I defined above, the phi star, is actually going into the braid group on n strands, which is well known to project onto the symmetric group on n elements. And actually what we have here, so here is the standard projection, which to a braid associates the permutation of the strands. And this is a commutative diagram, which is explaining in which sense the phi star is actually a lift, an algebraic lift of the homomorphism F star. Now, the first thing we have to try to do is to give an algebraic classification of braided surfaces in the sense I gave you.
Sorry, can I ask? Sorry,
yes.
At the ramification point,
Yeah.
we can take holonomy of some arbitrary number of points can be changed, and maybe there are some regular disks. Yes.
Yes. Yes.
Okay. Mm-hmm.
Yes. Yes, you're right. And what has been done already in the case of by Kamada, by Carter and Kamada, and so on, in the case of this, can be automatically and easily extended to the general case of surfaces, namely braided surface classification is an algebraic one and is given simply by the holonomies, by this invariant I defined here, phi star, which is a homomorphism into Bn. Of course, we have to take care of several things. So again, we have the action, because we need it in order to define a homomorphism from pi1 of sigma minus B into Bn. We needed to fix a base point. Now changing the base point amounts to conjugate by an element with the braid group. So here is the action by conjugacy. And on the other hand, again, we can change by any homeomorphism of sigma minus B, So the mapping class group of sigma minus b is acting on the left side as explained here by this left. So we need to consider the orbit space of the mapping class group on the set of homomorphisms from sigma minus b into Bn up to conjugacy. And now I added also some star. This star is something a bit new because not all homomorphisms from sigma minus b into Bn can be obtained from such a braid group. You need some extra condition. This extra condition is coming from the constraints of the let's say of the embedding. So we would like to have, for instance, smooth surfaces. So our phi from the very beginning, I recall it's here, can be a smooth embedding, but it can be a PL locally flat embedding and so on, or just a topological. And I will say a little bit later which are the restrictions on the holonomy around these points. So these branch points have, let's say, gamma I is such a curve. Here is the base point. The holonomy of gamma I has to be restricted depending on the problem we are considering. And I will say a little bit more later. And now I can state what I obtained with my colleague Pagotto as a positive result in this direction. So the first theorem, I'll try then to give the main ideas of the proof, is that there exists some h which depends on n and m. N is the degree, and m is the number of the branch locus, number of branch points, such that for any degree n branched covering as to sigma, where sigma has genus big enough, so at least h of n and m, with at most m branch points, they occur as a characteristic map of some braided surfaces. That means that there exists a lift, and our braided surface is PL locally flat. And this is important because in the smooth case, one has to change something. And this is saying that you have a positive solution in the case where the genus of your surface is very large in terms of the degree and the branch point. We have no idea about who's that h of n and m. H of n and m, which is unknown. I mean, we have no idea if it's effective or not. Such a solution for the lifting problem has been given in the case of solvable unramified covers by Peterson in the 90s already. And this question has been asked and discussed a lot by Hansen in the 80s. And already Hansen observed, he mostly worked with the unramified cover. when he asked the question, he already stated some way to approach this problem, and he transformed the algebraic lifting problem, the geometric lifting problem, into an algebraic one as follows. So we have a surface. In our case, it would be a surface minus a branch point, but minus branch locus. But it is already interesting in the case where sigma is a closed surface. So we have a map from a surface into some group G. And the question, for instance, the main case which is interesting for us is when G is just the group of the symmetric group of n elements, and you have a bigger group surjecting onto G. And the question is whether you can lift the homomorphism, the group homomorphism from pi1 sigma into G to some group homomorphism phi to G tilde. And the two questions are essentially equivalent. This is the result of Hansen in the 80s, saying that exactly this problem in the case of the when G is Sn and G tilde is Bn is equivalent to lifting geometrically the surfaces into sigma cross R2 when we have unramified covers. And the way to see that this question is non-trivial is just to take now a surface which is closer and orientable, because now it defines a fundamental class in H2 of sigma, and to observe that there is already some interesting invariant out of that. This invariant is the image of the class of sigma, which belongs to the fundamental class of the surface sigma. So I recall sigma is closed orientable surface into the second cohomology group, the so-called Schur multiplier of the group G. And it is actually called, one calls that the Schur class of the homomorphism, which is this image into H2 on G. Now, one immediately see that this is kind of invariant of our problem. In fact, the automorphism group of pi1 of sigma is acting, as I said, on the left, on the group of homomorphisms from pi1 of sigma into G. And actually, it preserves Schur classes. It acts trivially on H2. So actually, what we get is already an invariant from that algebraic object I considered at the beginning, namely.
And Schur class coefficient modulo 2 or integer?
In this case, it should be integers.
Mm-hmm.
If you want to consider mod 2, then one should go to another theory which is working over non-orientable surfaces.
Mm-hmm.
And the invariant is in some sense weaker.
Yes. And
So,
what is geometrical meaning? You will explain of Schur class. What does it mean? Okay.
Yeah, I'll say something.
Mm-hmm.
I will say something about that. But actually, it will be embedded in kind of proof I gonna give. So most of the philosophy of what I'm saying now is that the essential invariant of homomorphism is just the Schur class. And if we're working with orientable surfaces, which are closed orientable, then the Schur class is essentially the only one invariant up to something. And I will explain now up to what? So in order to say something, I'm defining pinch maps between surfaces. Pinch maps lay on the opposite of branch coverings. Pinch maps corresponds to take a surface. Let's say I define here one of genus G+1, and I put here some one handle on the right, and now I'm crushing the one handle to one point. Okay, so this is giving you a map from the surface sigma prime of genus G+1 into the surface sigma of genus G, in which I crushed one handle to one point. The way to starting from a homomorphism from pi1 of sigma into G, or from a map from sigma into some space, for instance, into the classifying space of G, and adding up the map from pi1 of sigma prime G+1 into sigma G by this pinch, I call that a stabilization. The stabilization corresponds to go from a bigger surface, but not changing anything essentially in the homomorphism. It's just one part of the surface is get crushed, and the other one it's just the homomorphism we started from. And so actually we get another homomorphism which is corresponding, if I'm taking this curve out here, lying in the one handle, that the curve is sent into one. So here is maybe the main result about Schur classes and surjective homomorphism. Now observe that I added something. Of course, we need to consider surjective homomorphism, because if we are looking to homomorphism from pi1 and sigma into G up to some equivalence, then well, up to conjugacy on G and the action of the automorphist group of pi1 of sigma on the left side, the image of pi1 of sigma into G is an invariant of the situation. So we have to work with surjective homomorphism, and we are not looking to homomorphisms which are equivalent, but which are stably equivalent. So what this means? That means that there exists, so we have two homomorphisms from pi1 sigma G into G. Well, you can have a pi1 of two different surfaces, and then you get stabilizations, which are Hurwitz equivalent, meaning that you have pi1 sigma G plus some n, well, h, some big h, which is going into, by some iterated pinches, into pi1 of sigma G, and again in f by f and f prime. And we are looking here if these are equivalent, meaning up to conjugacy on the right side and the action of the mapping class group on the left side, they should become the same. So these are stable equivalent, and stable equivalence, the theorem by Livingstone and Zimmerman from the 80s is that this is the same thing as that the fact that the Schur classes do agree.
Excuse me, what is G? Is it a symmetric group?
It's any group.
Uh-huh.
It's any group here. And that is interesting. I mean, it's just later, in our case, we need to consider finite groups G, and for most often to be the symmetric group. Let me give you a sketch proof of that. So this is coming from this old theorem by René Thom, saying that if you take the dimension n orientable borders group of a space X, then you have a map which associate to any such borders class. So I recall you that that corresponds to, let's look to omega 2 of X. So I'm looking to surfaces. So this is surfaces into X. And I'm saying that two surfaces, F and F prime, are bordered if so F equivalent to F prime, if if there exists a free manifold and free. I said already here, with the boundary sigma union sigma prime, such that there exists a map from M free into X. In our case, X will be, as I said, actually a KG1, such that when you restrict F to sigma and to sigma prime, you obtain F and F prime. So this is the borders group. You working with in the orientable case, so everything is orientable. So here we have orientable surfaces and free manifolds. And the key point is that you have to every class like that, sigma F, you have F star of the class of sigma. Well, it's just, you know, this map here, it's precisely constructed by the same idea as the Schur class. This is the element of H2 of X associated to omega 2 of X goes into H2 of X. What is completely non-trivial and in general not true is that, well, for n smaller or equal with 3, the map from omega through an X into omega n of X into Hn of X is an isomorphism. So actually, what is saying that if you are looking to classes, homology classes into X, for instance, I'm taking X to be the classifying space of G, then any class in H2 of G can be obtained from some surface which is sent by a map into X. It is represented this way. Okay, so because of that, now I can give you a short outline of the, well, I didn't have to take out everything. So here I'm taking my surface. So here is sigma into KG1. The surface sigma prime. And I assume they have the same. FF prime have the same Schur classes, Schur invariants. And what that means? That means that they represent the same class in omega 2 of X. So same class here. So there exists an M3 going this way with the map big F here. And now I'm considering what's called a Higard splitting. Higard splitting of the free manifold, which corresponds to some surface up here of big enough genus, which is, let's say, sigma G plus I H. And the fact that this is a compression body, so it's obtained from a surface, actually from sigma G plus I, just by adding one handles and the other one another compression body. So I obtain sigma G plus H. From sigma G plus H, I obtain sigma by crushing a number of one handles. This is corresponding exactly to the fact that the map from pi1 of sigma G plus H into pi1 of M into KG1 and this is precisely this corresponds to a pinch. So this map up here is corresponding to two ways. So we have two maps from pi1 of sigma G plus H into KJ1, which is corresponding to the fact that here we have one compression body, the red one and the green one, and these are glued together along some homeomorphism. So the way you present sigma G plus H as the boundary of one compression body or the other compression body is giving you two maps from pi1 sigma G plus Y into KG1. One is a stabilization of F, and one is a stabilization of pi prime, F prime. And these two are actually, because this extends to M3,
You mean these two maps are the same?
they are equivalent by the action of a homomorphism.
Mhm.
Because it extends to M3, the gluing map, let's call it by big pi of the two compression bodies. So I am taking a lift of it, and this is sending this pi1 of sigma G plus 1 into itself, make the stabilization of F. This is F1 and this is F2, and actually make F1 equals F2 composition, a lift of F tilde. It's an automorphism of pi1 sigma G plus H. Now there are some problems to take care, but looking at the base points and so on. But essentially, this is a proof that because of this theorem by Tom saying that the Borden's group of X is the same, is naturally, canonically isomorphic to Hn of X for in small dimensions, then every homology class, for instance, into H2 of G, which is the same as H2 of the space KG1, can be represented by a surface map into this classifying space, and then you extend it to the free manifold M3, then what you obtain going in this direction by stabilization and in this direction, the two are equivalent by means of the gluing map of this free manifold. So this is the sketch of proof. And in particular, this is giving you an immediate consequence on when a surjective map from pi1 of sigma into some group G is lifting, but now instead of lift normally, I'm saying lifts stably to G tilde, where I recall G tilde is any group which surjects onto a given group G. And if you want just to lift, I still don't know what the answer, but the theorem above is saying that if there exists a such lift stably, if and only if there exists a class A into the second homology of G tilde, such that so here is pi1 of sigma or sigma G tilde, and you need to find a class here A into H2 of G tilde, such that when you take P star of the class from here, you get the same thing as the Schur class in H2 of G. And this is essentially everything we know in this general situation, namely how to lift homomorphisms from a surface into a group to a bigger group. Now it was some progress in 2006 by Nathan Downfield and Bill Thurston, which are taking care of the case when when the target group G is a finite one. Namely, what are they saying is that if the group G is finite, there exists some G, which depends, of course, of the group, such that all surjective homomorphisms from pi1 of sigma into G having the same Schur class, they become equivalent if the genus is at least G of J. So now you have a result saying that you don't need any more to stabilize, which seems at the first reading very strong. But actually, the key step here, which is also using the fact that we have a finite target group, is that, so the key point is that if the genus of the surface is large enough, then actually all surjective map from pi1 of G into the group G are actually stabilizations coming from lower genus. So I put it at the key point. So the downfield has some extra results about that. And what we can observe is that in the unramified case, when you didn't have any branch locus for our branch covering, actually the theorem above plus the next lemma, it's already proving the theorem. So what's the next lemma? That's something very easy. Namely, if you look at the specific case now, when G is a subgroup of the symmetric group of n elements, P is the projection from the braid group to Sn, then at the level of second homology, then you have a surjective map. So once you have this lemma, you use the corollary, saying that it lives stably if and only if you have some diagram up here, you have the surjectivity at the level of second homology. So that means that if you have maybe I explain you here. I have a map from phi1 of sigma into some group G into Sn, and now what you know is that you have some stabilization. Well, you know that there is there exists a H2 of H2 of pi minus 1 G, such that P star of A is the Schur class of the map F. Now A is an element of H2, so it can be represented by some surface map. I'm taking a surface big enough. It's not so complicated to see that sigma prime, which admits a pinch into pi1 of sigma, and I'm lifting it that to pi1 to Bn. And now I am projecting down P, and I have a map phi I. And phi I of sigma prime, that's exactly the class A. So that means that if I'm taking here the composition, P composed phi I from pi1 of sigma prime into G has the same Schur class of phi I is the same class as Schur class of A. And now I said they can be further stabilized by 1 sigma double dot, and I arrive here, and these two F and P composed phi I are stably equivalent. But in particular, the map you get here out of, so it's F composed with pinches from here to here. Actually, it can be lifted. It's just because phi I and F and P composed with phi are stably equivalent. F composed with pinch is liftable to, because it is equivalent to, how I call that, to phi. So this is proving the theorem in the case when we have unramified coverings. In the unramified coverings, there are some simplifications, of course, and in order to see why this lemma is very easy, you just observe that you put Pn for the pure braid group and observe that you have a 5-term mixed sequence in homology, which relates the homology of G, of the finite group G, to the homology of the P inverse of G, of the preimage into the braid group. And you have here an element which is H1 of Pn, and you take the G co-invariance. But actually, when G is finite, H2 of G is a finite group. And on the other hand, you know the homology of Pn is generated by classes of the form aig with a different from G, and I is smaller than G. And then you have the action of G on this side, and you observe that this is a torsion-free group. So this map is trivial. It is zero because you have a finite group here to be sent into a group which is torsion-free. So that's a very general and easy to use method. What it remains to be done is to provide some method to prove a theorem like the one by Livingstone and Zimmerman in the ramified case. So, I have somewhere some. Let me add here if I have time, and let me go a little bit further. Yeah.
And if we have ramification case, the situation is opposite. So you have a sure class even for finite group. Yes.
Yes. Yes.
And you can show us an example, because because no example up to now. But if you prove that there is no any abstraction, no example, but now we have some more interesting, I hope.
Let me say it like that. One obstruction. So obstruction is that, as I said, you have this this branch locus pi. I'm putting here, and gamma I. So the first obstruction is coming from Kamada, and saying that f star of gamma I, in order to be, as I said, PL locally flat surface embedded, then f star of gamma I has to be what is called completely. So this now this is an element of Sn. Oh, sorry. Yeah, I'm not taking that. Taking pi star, and has to be completely splittable braid. Now I have to explain what means a completely splittable braid. So if we have a vibration, we lift F. So I recall you have the map phi, and I'm taking just yeah. I'm taking the preimage into sigma crossers R2. by P. I'm taking the pre-image of gamma I, and I am looking to what are the points. So over, as I said, in sigma cross R2, I'm looking, this is a fiber, and the fiber is corresponding to a number of points. These are the points, the intersection of the phi of sigma with the fiber R2. And I'm looking to the image of sigma, phi of sigma, and this is a braid, but this is a closed braid. So I'm it is phi inverse, no, phi of, sorry. Taking the inverse image of gamma I by P and its intersection with phi of sigma. This is contained in R2 time gamma I, which is a solid torus. And inside the solid torus, there is some link Li. So I try to define something up here. So we have a closed braid, as I said, because it is just a braid which is closing in the it is just the trace of so this is the closed braid Li. And now we called the braid to be completely splittable if is already trivial in S3 and what I put up here, and every component of, so I have something into S1 cross R2, or let's say into D2, every component of the link Li here is contained in S1 cross Dij. Here is a disk such that Dij are disjoint disk. Okay. So now I can say it like that. A completely splittable braid is a braid such that every component is contained into some, let's see, here is the solid torus, and here there are some smaller solid tori, which contain each one component. Okay. So they are living into different copies, which are parallel of this big solid torus. And the link, you can see it now. This is a solid torus, which is automatically and embedded into S3. And there's a link there, it is trivial. Now, the theorem of Kamada says that local monodromy of PL topological flat embeddings are restricted, are constrained to be completely splittable braids. So if you want to prove a theorem like the one above, you cannot only lift the map from pi1 of sigma minus b from Sn to Bn, but you need also to make sure that the lifts around the branch points are precisely completely splittable braids. Well, there are many examples of completely splittable braids. For instance, I'm using the usual braid generators. For instance, B1, B2, B3, B4, in B5. It is a completely splittable braid. And you can do much better. You can put here at any step plus minus one, plus minus one, plus minus one. And these are completely splittable. And for instance, B1 cube, it is not. B1 cube, B2 cube, it is not. And as a remark, just a side remark, if you want to do the same theory for smooth surfaces, smooth in the usual case, then one has to restrict it to something which is of the following form: B1, B2 up to Bn, and or B1 inverse, B2 inverse, Bn inverse, or conjugates. The completely splittable braids are invariant by conjugacy. So this is slightly more restricted. Okay, I will say something about how to define Schur classes for the case when you have boundary. Actually, most of these have been done by Catanese, Löhne, and Peroni in a paper of algebraic geometric nature. And
sorry, Luis, but
yeah.
maybe you can explain the difference between PL vocally flat case and smooth case. So what can be an example? If we have, for example, B1 cubed,
Yeah.
what happens? So it is it lifts to a PL locally flat braided surface, but not to a smooth.
No, it won't be, because yeah, where should I hold a second to put somewhere my comment. Yeah, sorry. Yeah, here. Okay, so what do you have? You have something of the following kind. Locally, here you have a branch point. And here I'm putting just something one-dimensional, but you should find that here is a fiber, and the fiber is namely, well, R2, or a disk, minus endpoints. So what is happening here is that, well, if I'm thickening a little bit, okay, here you have these points, and they are traveling around. And they are consisting of they can have several components. And I have a completely splittable link, which means that if it is like that, then what happens is that every component let's say that the boundary here, so here is a solid torus. What you see, let's put, it's a solid torus, which is the preimage. Here is gamma. Solid torus equal preimage of gamma. This is the red part, but I'm sorry, let me make it in two different colors. Okay, so around here you want to find a D4. The lateral surface. This is lateral surface. It's lateral surface is a solid torus, which is the preimage of gamma. Okay, and the cups up and down are corresponding to the green part. Green part you can see here as is also a solid torus. But it's actually, you want that map P from D4 into D2. You want it to be a when restricted. To sigma, a ramified covering. So actually you have here, when you have a Li, let's say L1 component, you want L to bound the disk, and you want that under the projection bounds the disk, but this disk is up here. It is embedded somewhere into D4, such that the restriction of the projection D4, when you restrict to the projection to D2, from D2 to D2, be just a ramified covering. Over D2, ramified at P. So you see that here, the embedding, the way the boundary of D2 can be into this solid torus is not arbitrary. And in some sense, it has to go anytime, just once a twist on a side or on the other side. So for instance, B3 cannot do that because B3 is twisting too much. The restriction to the disk, B3 is still bounding a disk, but the restriction of P to that disk is not anymore a ramified covering, because it's having what is a ramified covering? That's a surface without, let me say it, is ramified covering is a map without folds. So if I'm look at it as a map which sends every triangle into a triangle, so it's non-degenerate as a simplicial map. So you can put some orientation on the triangle so that you don't have positive and negative triangles sent into the same. So actually, a fold is to have two triangles. Two triangles which are sent into the same. Okay. So this is a fold. So you have a ramified covering if you don't have folds. And actually, if you have twists in the braid which are going too many times, well, I know I have to be more precise there, but the idea of the proof is that if you go too many times around, like in B3, then it cannot be just once. Here you need to have some fold. So that's the reason to get, and here you have also two things. This is the PL case, the PL locally flat. But in the smooth case, you need that this to be smooth. And if you go on one direction and then on the opposite direction with the braid, at some point you get a point where it is not anymore C1. I don't know if it's enough. This is part of the Kamada theorem. So I won't say it much. It's already 1 hour and a half, and I realized that I didn't go through the proof of the first theorem yet. I'm sorry. I'm quite. The speed is not that high. Do you want something more about that, or I can say a little bit more about how to define Schur classes?
Okay, yeah. Thank you. Go ahead, please.
So you told me I might go on for.
Yeah. You if you want, you can continue next time. That's an option.
Let's go ahead now. If you have still questions.
Yes, yes.
So actually, what we are doing in the case when you have punctures is already to remove some small disk around the punctures that are giving you surface with boundary. And now, when you look to these maps into from the surface minus, of course, the brain point, you can you find this surface with boundary, which is sent into the classifying space of the group G. And now I have to fix some loops in this space. These loops are corresponding to the conjugacy classes of which are fixed, this CI. I want now to prescribe the holonomies. I want to prescribe the holonomies into G, because when I go to lifting the homomorphism from pi1 of sigma to B, I have to be sure that the holonomy around the peripheral loops around gamma I are exactly the completely splittable braids, because otherwise I'm lifting to some surface, but actually it's not a surface. It's not something which is PL topologically embedded. It's just some the closure of it would be it would be a space, a topological space, but the closure is not necessarily a surface anymore. So again, I'm taking the Schur classes, which is the image of the now the fundamental class of the surface with boundary, and I'm asking that the boundary loops up here of this surface, yeah, they are sent into some fixed loops into KG1. And if this is a problem because they are not anymore embedded and so on, then there is no problem. I can take here the product with.
Sorry, can I ask? As I understood you, we have some more easy problem comes from linking number. Probably this is a Schur class because if you take some copy of component, then we have to do over the ramification point with prescribed order. We have to keep, for example, if you have a prescription of order Q and then other are regular, a regular lift has to be unlinked with each other and with this fiber with spine pi time. So it's some but probably there are more difficult abstraction comes from the spanning when we have some non-trivial link and we cannot take a regular point of ramification.
Exactly.
And you can do combination of all abstraction in or you do some partial abstraction interpretation with Schur class, and this is not total class, or you have some universal description of the problem. I don't. Can you more? Can you give? If can we take such an example? If you take three link and one is rotated around two others, so the linking number between over the closed loop are non-trivial. It means that if we have we cannot do the regular position of the surface because we have self-intersection point in this in the middle point of the disk, or this is not possible and abstraction is more delicate. Can you explain something easy thing?
I think the abstraction is a bit more delicate because it has essentially two parts. Let me see if I yeah. Second. Just want to add one more page. Yeah. So what I'm climbing is that already there is a lift to instead of considering the Schur class just into H2 of the classifying space of G, because you have a surface with boundary, then you fixed, as I said, the conjugacy classes. CI in G, or if you want C into G to the power M, up to conjugacy. And here I want to, so I'm fixing gamma I, the peripheral loops. and I'm fixing the classes CI. And now I am taking some loops in KG1. Let's say if I want them to be embedded, I'm taking the product with R3, which are corresponding to classes representing the classes CI, conjugacy classes in G. So now we have a map from sigma and the boundary of sigma. Let's imagine that this sigma is corresponding to these are the conjugacy classes of gamma I, and this is a map into KG1. But now what I'm asking is that this is sent precisely into this link here. So instead of considering the class into H2, that would be into this space, H2 the FKG1, essentially times R3, LC. But LC is a copy of circles. And if I'm calling that H2 of G fixed by G, then we have some part of the you have an exact sequence H2 of G into H2 of G C into Z to the power M into H1 of G. Something like that. So the obstruction, if I fix everything, fixing gamma I and CI along with LC, provides a Schur class SC of F, which belongs to into this group H2, which is Z of C. And I suspect that part of that is also coming from this what you claimed about the linking number is related also to Z to the power M, and of course this depends on gamma I, Ci, and LC. If you want to make a Schur invariant which does not depend on anything, then you have to identify. You have to identify a number of, for instance, the conjugacy class already is saying if I'm changing the conjugacy class, you observe that this is sending into. So here is this is C1 Cn, and this is A C1 A inverse A Cn A inverse. And these two are not exactly the same group. I mean, they will be isomorphic, but they have to be identified if you want a coordinate-free description, which does not depend on the choice of gamma I and Ci. And what we can show is that fixing this structure, then the Schur, these Schur classes are also distinguishing precisely the homomorphisms up to stable equivalence. But when I'm taking stable equivalence, there is again a subtlety. Yeah, stable equivalence. So I have a surface, a number of branch points, and genus, and I don't touch at all this part, but I'm just adding an extra one handle, adding extra one handles, because there are also some other kinds of equivalence when I'm stabilizing by adding more points. So in some sense, I would say that part of the obstruction is vanishing when I'm adding enough one handles, even if at this side it doesn't look so. So there are, of course, many other small complications. I can explain some of them. So the equivalent of the Livingstone theorem. Let me.
But linking number in your diagram involves in Schur class or is comes from pi one. Is the simplest Schur classes? Yes, linking number or
Right.
or not?
Is not not full. The full linking number is
not full, but maybe most primitive. But this is example of Schur class, yes, or is not an example. I don't understood your diagram previously. You have.
Yeah.
Can you show? Yes, z in power m is in H1 or inside H2. This cyclic.
It's essentially in H2.
Okay, thank you very much.
Because well,
yes, I understood.
In order to do that, you have the classes CI, but you have an obvious condition. The product of the classes CI, in order to have you have imagined, so here is these are the points. So here is the product of CI, the holonomy of the product of CI. In order to be able to put a surface here and to extend to this surface, this has to belong to the commutator. Okay. So this is a necessary condition for being able to extend the map from the fundamental group of disk with points to some surface, to some closed surface. So again, you have this kind of. Let me state briefly how the results should work. To see in the first proposition, I would say that for finite G, you have an analog of the Livingstone Zimmermann and also let's say G finite. There exists G which depends on G and M such that any surjective, any two FF prime which are going from pi 1 to sigma G minus B into G with G bigger than our lower bound, such that f of gamma I equals f of gamma f prime of gamma I equals Ci and have the same classes, Schur classes. which belongs to, as I said, H2, G, and C. Then, you know, there is a way to add handles here in order to identify the classes of gamma I, which are on the smaller surface to classes on the higher surface. So these are just more subtleties. Then F and F primes are equivalent, are stably equivalent. Well, no, yeah, are equivalent. Sorry, are equivalent. That's it, the analog of the downfield Thurston theorem up to. So I said the action of gamma sigma minus B times the action by conjugacy by G. So this is precisely the same result. There is something very similar in which instead of this invariant, I define it in purely geometrical terms. There is one which is the epsilon class still associated to F, which is defined by Catanese, Leone, and Peroni, which is the image of this Schur class, as I said, somewhat non-canonically, into something which is essentially H2 of KG1, and you take here the one skeleton. Okay? So this is, well, essentially, I'm skipping something. And already that invariant was good enough in order to prove this, this theorem. And this is partly done by Catanese, Leone, and Peroni. And this is exactly their proof of Zimmermann. You just add the G finite here. Now, to see what's going wrong is that you need to be able to lift now with constraints everything. So the constraints are of the following form. You take, let me put it like a lemma, which was missing. You take sigma, a couple of permutations, and you want the permutation to belong to the commutator. Then you have to prove there exists actually there exist many, some lift and call it sigma tilde, which is now a couple of braids, such that in the first place, the lift of every copy, sigma e tilde, which is an element of the braid group, is actually a completely splittable braid. So this is the first constraint. The second constraint is that one need, of course, to have that this is an element of the commutator. So one has to be careful what happens when you look at the image of this element into the Abelianization and to correct somewhat. And the first thing is that if you have a pair of elements, let's say sigma I and sigma G are actually inverse to each other, then you take their lift to be inverse to each other. And if you are able to do that, this is a purely combinatorial question, then everything which has been proved before in the unramified case goes on for the ramified case using this proposition. As I said, this proposition, this is a mixture between Dunfield and Thurston, and the old theorem of Livingston and Zimmermann. And as I said, there is also a version by Catanese, Leone, and Peroni, which is quite similar, and it can be used instead of our definition. But our definition has the feature, the nice feature is that you can see that that's exactly a Schur class in a geometric way. That of Catanese, Leone, and Peroni is a more algebraic way to find the same, essentially the same. To prove such a lemma, well, this is just, as I said, you have to see which are the completely splittable braids. Essentially, you take for a permutation, sigma I permutation, you divide, you take a product of cycles. And essentially, you want to lift cycles. And the way you lift cycles is the so-called Mikado braids. So what is a cycle? If I'm putting the cycle to be 1, 2, K, then the usual lift would be B1, B2, BK. Well, this is not well enough. And actually what I have to put here is epsilon 1, epsilon 2, epsilon k. And if epsilon I belongs to plus or minus 1, then there is always a way to make the arrangements such that these become completely splittable. They are always completely splittable braids, but you can arrange them to be able to satisfy this condition and the third one. I would say this is not very geometric, is between combinatorics and algebra. So this is mainly the way to prove in the general ramified case. I would say a few more things if you want to see why this might be interesting, is that if you take such homomorphisms which are called elementary, namely those which have the Schur class trivial, the question which is corresponding to how many stabilizations are needed to make two surjective homomorphisms. Sigma G or sigma G minus B, as you want, into some group G stably equivalent. This is equivalent to ask, in the case when the class is 0, if it factors to the free group. Because if I'm taking the handle body, HG, obtained by one of the handle bodies, by gluing handles over the surface. So this is HG of genus G. Then of course maps which are factoring through a free group have Schur invariant 0. And this is the simplest way to construct such such homomorphism. So the question is whether all are arising this way. And sometimes for very specific groups, and here are some groups were defined by Novikov. Maybe take the simplest case, take Z or take Z over MZ, and then you take a binary tetrahedral group and so on. Then any such homomorphism is actually factorizing. That's a theorem of Sasha Reznikov, the late Sasha Reznikov, who proved that all such elements, because H2 of such groups is zero already, so all homomorphisms have a trivial Schur class. Actually, all of them are factorizing through a free group. So for the moment, what we know is that if the group G is finite, there exists some genus such that for any group G fixed, all null homologous surjective homomorphism from pi1 into G is elementary for genus which is large enough. Now, of course, this is saying that we have some kind of invariant. I think first time it appears was by Livio Liechti and Marché. The thickness of null homologous homomorphism or class is actually the smallest genus of Higard surface of M3, which is to which the homomorphism is extends. And actually, we can explain exactly this. This is precisely the number. So if you are in genus G here, and the Higard genus is G plus H, then H is the minimal number of stabilization you need. You have kind of an algebraic way to compute it, but this is completely useless, I would say. This is coming from the Hopf formula, which is giving you a way to compute algebraically H2 of a group in terms of group presentation. Now, I wrote here a formula, but I won't say too much about. But instead of that, I would say that there are infinitely many groups for which when you take homomorphism from the pi1 of sigma into that group, and these are PSLN for with coefficients in the finite fields F cubed. And if I'm taking such epimorphism, such surjective homomorphism, the kernel does not contain any simple loop. And in particular, they cannot be non-elementary. They cannot be elementary, because if I have a pi1 of a surface which is sent into a free group, then it is known by some lemma due to Jaco, Stallings, Zishang. It will factorize through the pi1 of some handle body. And in this handle body, you have here some curves, which are simple closed curves, which bound disks here. Okay. So if there is no simple loop in the kernel, that means that it cannot factor to a free group. So you really need to stabilize at least once, and this for an infinite family of groups, which are also simple, characteristic, non-abelian, etc. And this was already particular cases were proved by Gabay, Livingstone again, and Picard. I think I already did that for 2 hours, and I'm sorry, I'm going not so fast. So I should better stop here. 2 hours. I think it's a lot of patience you had with me.
Okay, thank you very much, Luis.
You're welcome. There any questions?
So you had this z to the m, where you had this sure relative sure class, yes, modular.
Yeah, but even this part is rather trivial in general. I mean, in the case when you have also ramifications, if you force the ramification, what is really important is that the ramification be forced to be a completely splittable link. In order to, that's the main. And I think that this is also forcing immediately that the linking number you are talking about to be 0.
So my question was, why is it z to the m? So m is the number of branch points, but we also have n, which is the degree of the covering. And,
Yes,
and
m square minus m half, m over 2, something like this. So, pairwise linking number, as I understood, not much more than n. And this is not interesting, as I understood. Much more interesting problem looks more complicated. Sergey, is it okay? My or I understood nothing.
No.
Linking number is not very good stuff in this problem. To consider interesting example, we have to take any higher linking number to demonstrate that some ramification covering is not a prem. We are looking for explicit example. We have take an interesting example which is not prem, and as I understood, we have to take something which is not relate with linking number, because on the level of linking number we have no any interesting example. What I understood, but maybe you tell me that it's not so. I will finish. Sorry about my expression.
So what I understood from you is that you want to take a braid and to look whether that braid extend to part of PL flat surface over the disk. But what I'm saying is that already Kamada is saying that this link should be trivial. So the linking number should be all trivial.
And this abstraction link should be trivial. This abstraction involves some higher commutator, as I understood.
Involves our kind of higher commutator, right?
Okay.
That's that's the way it arrives in H2. Yeah.
okay, that probably answers my question as well.
And this Kamada abstraction is stable in your sense. So you cannot kill a Kamada abstraction even if you take some summation with loop, with handles outside of.
No. That's true. This is stable when you add one handles.
And unstable abstraction what is a what it's look very very complicated, and you told only on the stable abstraction is understood, because non-stable abstraction is not so easy to, not so interesting. There are many.
What I said is that unstable abstraction should be much more subtle,
Much more.
more complicated. And the only thing I know is that as I said, for groups, I'm just looking to the case where the lifting problem in general is complicated also when you try to lift to the braid group. But if you are able to lift to the free group, then of course you can lift to any braid group, to any group in fact. So I was looking just to this problem. I'm taking a group G, it could be finite or whatever, and I'm looking to an element which has trivial stable abstraction, trivial sure class. Can it be lifted to the can be lifted to a free group? And what I know is that sometimes this theorem by Reznikov is saying that for whatever group and whatever homomorphism you get from this class of groups, which is a very interesting class of groups, as I said, binary tetrahedral, there are finite groups. Binary tetrahedral, binary icosahedral, binary octahedral, dihedral groups, then it works. You can always lift to the free group, so then you can lift also to a braid group.
Yes.
But I have another family of examples which are, I need more time to explain, but it is coming from the so-called quantum representations of mapping class groups and so on. So there exist elements like that and groups such that any homomorphism which I define cannot be lifted to a free group because it has no simple closed curve in the kernel. So for this, it cannot be lifted to the free group. I don't know if it can be lifted to the braid group because I have no way to check geometrically. I can show you why it cannot be lifted to a free group. As I said, it cannot be lifted to a free group because there should be, it is no free homotopy class of curve, of simple closed curve, which is sent in, which belongs to the kernel. And that because I was able to compute for any simple closed curve, what is the image in this group? And the image is of some non-trivial order, let's say some p different from 1. So it cannot be in the kernel. And this for any simple closed curve. So this is the only method I have to check that something does not lift. And it doesn't work in general. It works for a huge family for an infinite
Yes,
family
I see.
of finite group, but yeah, I don't know others. So
And this nice group comes from there are some characteristics of this nice group which satisfies this problem. Probably this is a fundamental group of something class of spaces and so on.
In the case of Reznikov, there where it can be lifted, these are groups of, for instance, free manifolds
Mhm.
which have a magic of positive scalar
Yeah.
curve,
Okay, so it's act on a sphere.
right?
And yeah, this is a very nice class of group. Yeah, and quantum group is some. So there are more complicated. Okay. Mhm.
These are more complicated. These are much bigger.
Yeah.
And this comes from the representations of mapping class groups. And if you take a mapping class group of a surface with a puncture, then the fundamental group of the surface embeds into this group.
Mhm.
Right?
So
And then
it's but a Rybnikov group is are finite group, and this quantum group are infinite or also.
yeah,
Okay.
they're infinite in general. And I'm taking the image into some group which belongs to the image are matrices with coefficients into, let's say, into some cyclotomic field. And then I into a cyclotomic ring of integers. And then I'm taking modulo something to get it to become finite.
And are there some interest in huge group comes from crystallographic higher dimension crystals? So it's called how monster group, or it is not in this direction. There are finite group, but very complicated. No.
I was not able to construct surjective homomorphism into this kind of finite group. The only class of groups is coming from you take linear algebraic groups of the unitary type or of unitary indefinite or not, and you take reduction mod p or for some p.
Mhm.
And what I get in general, there are also either unitary groups over finite fields, or DSLN over finite fields, or even more complicated rings, but finite rings.
Mhm.
That's the only class I get. So are finite groups of Lie type, and are very particular. And I was not able to find anything from the sporadic groups or whatever.
Mhm. Mhm.
I don't know how they can arrive.
Yes.
Conjecturally, all of them should be found, or all but finitely many, all
Mhm.
finite simple groups, but I don't know.
Mhm.
Are there more questions? Okay, then, well, thank you again, Luis. It was a very interesting talk.
It was a pleasure to talk with you and to give a talk here.
До свидания, спасибо большое.
Спасибо.
Thank you. Goodbye. Goodbye.
Bye bye. See you.
Yeah.